Today we are looking at finding volume with cross sections. We are now going to do calculus in 3 dimensions here. This is a tough one to do through a video. This one needs a lot of kind of physical demonstrations, which is probably why I haven't made a video of it before. But I'm going to do my best here. And of course, as always, if something is confusing, as we go over things in class, please feel free to ask. So over on the right, you'll see that I do have your notes out here, but before we get to those, I kind of want to jump over here to the left, this GeoGebra tool that I have, just to kind of give you an idea of what it is we're trying to accomplish here. So here's how these problems work. We are building a 3-dimensional solid that is made up of cross sections that are a particular shape. So if you look at the example here in your notes, you'll see this kind of 3-dimensional figure. I don't even really know what to call that shape. But if you started over here at this end and started taking slices, all of your slices would be shaped like squares. They would get smaller and smaller and smaller, and those squares are kind of defined by this sideways parabola that's down on the bottom of this graph. That's the idea, is we're going to use graphs to define the base of a figure, and then we're going to build a solid using cross sections. So now let's take a look over here to the left, and maybe I'll make this a little bigger for right now. There we go. What I've got here is 2 functions. I just picked 2. So I've got the sine of x function and x squared minus 1. Let me drag these to kind of show where our endpoints are going to be. Our endpoints are, the boundaries of where we would find the area. So like right now, I feel like I could ask all of you to find the area of that yellow section and you would be just fine. Okay. What we are going to be doing is we are going to be inserting square cross sections. We're starting by talking about squares. And this purple line that's drawn here that says base 1, that's like the side of the square. Okay. So let me show you what that would look like. Here's one square kind of wedged in there. Okay. And I can move that square up and down, so I could put it down here. Notice it gets smaller over there because if you look over on the left, the base is getting smaller. The distance between the graphs is getting smaller. And then here it's bigger again, here it's smaller again. And the idea is we're going to fill this space with squares. So watch this. So there's kind of the start of my 3-dimensional solid. I have all these square slices. And if I make more and more and more and more and more slices, it eventually takes on the shape of a solid. Okay. Now this is a weird shape, right? This is not something that we have a traditional volume formula for, but calculus will help us out with this because what we can do is use some algebra to find the area of just one of these squares. So once again, if I go back to just one of these squares, I can find the area of this one purplish square, and then I can integrate. And when I integrate from A to B, right, my 2 endpoints, A and B, what I'm really doing is adding all of these squares together and running that limit to infinity, meaning I'm filling it in as a solid shape. Okay, so that is sort of the process, is we build the cross section, we write an expression for the area, and then we integrate it from end to end, okay, depending on the graphs that we're given. So we're going to start with squares. We'll probably spend quite a bit of time just talking about squares. And then once we talk about squares, we can talk about these other shapes. You'll see some other shapes listed over here, the rectangle, the semicircle, all of that, because the process is similar. We just have to change up how we're finding that area. Okay, back to split screen here for a quick second, so I can again kind of talk through this process. So this is what we just talked about. We said that to find the volume of any one of these figures, we're going to find the area of the cross section and then integrate from A to B. And A and B are the end points. So you'll notice I adjusted those to these intersection points because this is where my base of my figure is defined. Okay. As far as finding area, this just relies on you knowing your formulas from geometry. And so let's think about that square here for a second. Let me cut this back down so we're not seeing as many squares. In fact, I'll just turn it so we're just seeing the one. The area of a square is found by doing the side length squared. So actually down here in this table next to square, we're going to write down area is equal to side length squared. Okay. That's how I would always start one of these problems, is just how do I find the area of whatever my shape is. If we're worried about this side length, though, what I really need to know is what is the length of this purple line, right? Because this line represents that base over here in my 3D figure. Whoops, I'm dragging B around. Didn't mean to do that. But that represents the base in my 3D figure, okay? So the distance between this top point here and this bottom point here is just the distance between f of x and g of x, right? So the length of this side, my side length, is just f of x minus g of x. So I'm going to kind of jot that in here too. By the way, that's written up in that box for you as well, right here. Side length is f of x minus g of x. So the idea is, and we're going to kind of build this integral in little pieces. The idea is we want to integrate from whatever a is to whatever b is, this s squared, right, my area formula. And what that's actually going to look like is an integral from a to b. And instead of s, I'm using this. So f of x minus g of x squared. That's the formula for finding volume using square cross sections. Now, if you're going to try to do this by memorizing formulas, this is going to be really difficult for you because a lot of the formulas look very much alike. So you really have to kind of start each problem and run through that process like we did. Maybe you don't have to write it all out, but this is how I would think about it. How do I do area of this figure? What's my integral look like? And then if I figure out what my side length is, how do I actually put that in calculus notation? The good news is most of these are going to allow you to use a calculator. So actually I'm going to fire up a Desmos window here. You probably will need Desmos for quite a few of these, or your graphing calculator. Whoops, Desmos is a little out of my screen here. I have to slide that over, zoom that out some. We'll figure that out. Okay. So I actually think I'm going to be jumping around in these notes quite a bit because I don't love the order that the examples are in. But let's just start with this one here, with example 1. Maybe I'll shrink up my Desmos a little bit so we can get my whole example in there. Okay. Find the volume of the solid that is bounded by the function y equals 2 sine of x and the x-axis. Okay, starting with square cross sections. So first thing I want to do is just look at this thing. I want to type in, I might do f of x equals 2 sine x. Now, the way this question is worded is a little bit vague. You've got a lot of places where there's area that's bounded between the function and the x-axis, right? I could be talking about this. I could be talking about this. I could be talking about this. But all of them are congruent, so it doesn't really matter which one we use as the base of our figure, okay? So first thing I would think about is just what are my boundaries, right? What are the boundaries of my area? So if I'm using this first bubble of space, my endpoints, and remember my second function is just the x-axis. So that's why I'm looking at those intersection points. This is just going from 0 to pi. So to set up this integral, I'm going to say volume equals an integral from 0 up to pi. And then I want to think about what f of x is and what g of x is. Well, f of x is just this thing, right? The 2 sine of x. G of x in this one, they didn't give me a second function to intersect with. I'm just intersecting with the x-axis. So my g of x is actually 0. Okay? So inside here, I'm just going to say, let's do my f of x, my sine of 2x, minus my g of x, which is 0. And then take that whole thing and square it. So this thing here is my side length, right? Like if I were to draw a line from here down to the x-axis, anywhere in this bubble of space, this would give me the length of that line. And then I'm squaring it to create those three-dimensional squares popping out at me. Okay? Oops, almost forgot my dx there. And then I'm just going to jump straight into Desmos. I do want to point out, whoops, let's see, 0 to pi. I don't really need the 0 here. I'm putting it in for emphasis because a lot of the times you will have questions where it's two different functions. Just make, oh, no. Oh, I wrote that wrong here, didn't I? Whoops, this is supposed to be 2 sine of x. Sorry about that. 2 sine x. Sorry if you're yelling at me through the screen right now. So 2 sine x minus 0. And then on the outside of this, let's square that and put my dx. And there is my answer, 6.283. That's the volume of my solid. Let me hop back to our kind of visualizer here so we can look at this same one. By the way, you don't have to be able to visualize these. I mean, I'm happy to share this GeoGebra tool with you. You don't need this to be able to do the math, but I just want you to see the figure that we just created. Okay, so I made my endpoints go from 0 to pi, right? That's where these things are. Let me tilt this upward. Okay. So here's my 1 square, right? This length, and I can move that around. This length is always just sine of 2x. That's where it comes from, minus 0, because we're looking at the x-axis, right? And then to make it 3-dimensional, I square that. And so what I'm doing when I integrate, let's throw some more squares in here, is creating this weird looking shape that looks kind of like this. And that is the thing that I just found the volume of. So that's the idea with squares. We're going to try one more with squares, and then we'll talk about some of the other shapes. And then I'll probably do a second video to talk about circles, because circles do get a little trickier. Okay, let me head back to Desmos here. Let me clear this out of here. And let's head down to example 2. And now would be a great time to pause the video and maybe try to get this integral set up on your own. If you can't, you can stay with me and we'll do it together. So these are my 2 functions. Let's put them into my graph. Notice how I'm always naming them f of x and g of x, because that makes it easier to work with later on. Oops. Need the x squared off to the side here. There we go. Okay, so I'm working on this tiny, tiny little sliver of space, right? This area that's in between here. That's what I'm trying to integrate, right? I'm building square cross sections here. So let's see. My integral is going to go from 0 to 1. And I'm subtracting the green function minus the purple function because the green one is on top. So this one should be f of x minus g of x. But let's talk about why that matters even less than it did when you did area. When you did area, we said it's fine if you subtract in the wrong order. You can just make it positive at the end. Here, once you subtract, you're going to end up squaring that value anyway. So it doesn't matter even a little bit if this comes out negative, because it's going to get squared in the long run. So you can always just say, I'm going to do f minus g, even if that's not really the one that's on top. Okay. So let's see. Integral 0 to 1 of, and because I named the functions up above, I'm just going to type them in like that. I had to do that graphing anyway to be able to see where my endpoints were, so I may as well use it. And this one has a very teeny tiny volume, which you have to remember, this is a really teeny tiny shape here. So this volume is 0.039. Technically that would be like cubic units, but because I didn't give you any sort of unit here, I'm not going to stress about it. Okay? Okay, so the next question says, how would your answer look different if the cross sections were isosceles right triangles? Well, let's talk about where isosceles right triangles come from. Isosceles right triangles means that 2 of the sides are equal to each other. If we start with a square, we have 4 sides that are equal to each other. So if I cut this thing along a diagonal and get rid of 1/2 or the other, what I'm left with is an isosceles right triangle, because these 2 sides are the same. So essentially, I just took my area of my square and cut it in half. Okay? I'm trying to decide if I want to go back to the other page of notes. Yeah. Let's talk about this third one, and then we'll do both of them at the same time, just to minimize paper shuffling. So we'll talk about that in terms of a formula in just a second. Let's talk about this one. What if your cross sections were rectangles that were 3 times as tall as they were wide? So here's the thing with rectangles, is you're used to rectangles having 2 measurements, right? A base and a height, or a length and a width. But you can't integrate with multiple variables. So with these problems, they're always going to give you dimensions in terms of the base, right? So if this is our side length, right, same as when we were doing a square, they're going to tell you this is, 3 times as tall. Well, then that makes this 3s. And so for this one, my area would be 3 times s squared. For this one, by the way, we said it, but we didn't write it. Our area would be 1/2 s squared. Oh, I'm working with a dying pen here. But 1/2 s squared would get us the area of that triangle. Okay, before we do these problems, let's head back over to the first page of notes where we have that table, and let's fill in some information there. Shortcut my Desmos a little bit so you can see what's going on. Okay. So when we have a rectangle, the area is always going to be where one side is a multiple of the other side. And so you're always going to get that number, like in that example we just talked about, there was a 3 in front, right? So this is going to be written as k times s squared. It's always going to be some multiple times s squared. Well, that k is just a number, right? So when we write our integral, we can pull that k out front of the integral. So notice it's exactly the same as the square. It just has this number out in front. Okay? And my side length is still defined by f of x minus g of x. That's actually true for all 3 of these. The square, oh, I picked up the bad pen again. The square, the rectangle, and the triangle. All 3 of those have the s. Oh my gosh. All 3 of those have the s being f of x minus g of x. Sorry about this, guys. No edits, no edits. All right. Okay, that's true for all 3. So when we write this integral for real, it's just k times that same integral of f of x minus g of x squared. And the triangle is not much different because the triangle is just a special case of this. The triangle is always going to be half of the square. So then this would be 1/2 the integral of s squared, which is just 1/2 the integral from a to b of f of x minus g of x squared. See what I mean? That all the formulas start to look alike. So I would not try to memorize. I would make sure you understand why I'm using a 1/2, why I'm using a k. Okay? So let's head back to that example. So for this one, let's write out what our integral should look like, and then we'll use Desmos to get our answer. If we're just making triangles, it's going to look exactly like this, except it'll have the 1/2 in front. 0 to 1. And if you're thinking that's just going to take this answer and cut it in half, you're absolutely right. I can just jump over here where I have this in Desmos and type in a 1/2. And that's what my answer should be. So that would round to 0.020. And for the rectangle one, same thing. You're just going to put a 3 in front. Whoops. Minus g of x squared. And I can just go here to Desmos, knock out that 1/2, turn it into a 3. Okay, so I get what? 0.118 So that's it. So rectangles and triangles are really just extensions of a square. If you understand the square really well, the rectangles and the triangles should be no big deal. Okay, the circles get a little uglier just because the area formula is a little bit uglier. So I'll save that for the next video. But if you wanted to go try a couple on your own right now, you could jump to your homework and start working on anything that deals with squares, rectangles, or triangles, and then maybe come back and watch the rest of the video talking about circles.